workshop. It has been, a kind of a really exciting week for me, and we have an exciting talk for today. So our speaker is Katie Craig, who is coming from UC Santa Barbara. Is actually still there, right? And she'll be talking about gradient flows in Wasserstein metric from discrete to continuum via regularization. Again, as before, if you want to ask the question, you can either raise it in the chat or you can just speak up. It worked pretty well thus far, and we are not in a hurry, so just feel free to turn on your mic and speak up. Please, Katie.
Thank you very much, Dejan. Thank you for that introduction. And yes, just to echo what Dejan just said, please stop me at any time if you have questions. I'm attempting to give the presentation on my iPad, so I should even be able to write or anything like that if further clarification is necessary. So like Dejan said, today I'm going to be talking about gradient flows in the Wasserstein metric. And the theme for my talk is going to be from discrete to continuum via regularization. And my mission for you today is that many of you, especially those of you from outside mathematics, may have already been persuaded that the Wasserstein metric is something that can be useful in applications for comparing probability distributions that arise in image processing, machine learning, and elsewhere. And one of the reasons for this is that the Wasserstein metric respects the underlying geometry of your problem. So whatever distance you have on your underlying space, the Wasserstein metric lifts that to the space of probability distributions. And so because of this, it gives you better tools for passing between the discrete and the continuum. So in today's talk, my hope is to persuade you that the same is true of Wasserstein gradient flows, that just like the Wasserstein metric allows you to pass between discrete and continuum, so does this Wasserstein gradient flow perspective also gives you new tools for doing that. And here, by discrete, I mean a system of ODEs, and by continuum, I mean a PDE. So, the specific problems I'll be talking about are based on two joint works. The first with Jose Antonio Carrillo at Oxford, Francesco Patacchini at IFB Energies, Karthik, and then the second is with Karthik L.M. Vasuthi at UCLA, Matt Haberland at Cal Poly, and Olga Turanova at Michigan State. Okay, so here's my plan for today's talk. I'm going to begin by giving a little bit of motivation for the class of PDEs that I'm going to consider. And this motivation comes from two applications. The first is sampling and probability. Given a probability distribution, how can you draw a finite number of samples from it so that as you draw more and more samples, you approximate the probability distribution more accurately. And the second application I'll have in mind comes from robot coverage algorithms. So imagine you have a fleet of robots, maybe a fleet of robotic bees or something like that, and you want them to evolve according to a desired distribution. What is an algorithm for doing that? So it turns out that both of these problems, a good way to develop algorithms from that is PDE principled algorithms. And I'll talk about some classical approaches for that using the Fokker-Planck equation and Langevin dynamics, and some new PDEs that can also help solve the same problem, degenerate diffusion equations. So these are the PDEs that we'll be interested in today. But because of both of the applications we have in mind, what we really want is we want a deterministic particle method for approximating solutions of these PDEs. Unfortunately, deterministic particle methods for approximating diffusive equations can be difficult in general. And so that's where we'll really be leveraging this Wasserstein gradient flow structure that gives you really good tools for defining particle methods. Particle method is fundamentally a system of ODEs that describes where your particles are going, and the Wasserstein gradient flow structure allows us to connect that system of ODEs to the actual kind of PDE that we had in mind for our original problem. So at first glance, a Wasserstein gradient flow structure, the correspondence between that or the ability to use particle methods for Wasserstein gradient flows almost comes immediately. And we've heard this a few times in this conference already. But it turns out that the specific gradient flows that I'm going to be interested in, they fail the normal conditions you would need to ensure that the particle method converges. And so that's why the main point of my talk today will be how you can combine a particle method with an appropriate regularization to get, a regularized particle method, or in other words, a blob method for these diffusive equations. So this will allow us to use this PDE principled approach to get a deterministic particle method for these sampling or robot coverage algorithms. And the main result that I'll be talking about today is that this particle method indeed converges to a solution of the continuum PDE. Interestingly, and also relating to some previous talks that we've heard this week, it turns out that this blob method, this regularized particle method, which we developed from the perspective of trying to simulate these diffusive PDEs, turns out to exactly correspond to the mean field training dynamics for a two-layer neural network with a radial basis function activation function. So I'll describe that connection between the two. And so in that way, our convergence result showing that this particle method indeed converges to a diffusive PDE can perhaps shed some light on these models of two-layer neural networks in the overparameterized regime as the variance of the radial basis function goes to 0. And at the end, I'll conclude with a few numerics. Okay, so like I said, I'll start by talking about the motivation for our problem. Okay, so either thinking about it from the perspective of a sampling algorithm or a coverage algorithm, in both cases, you have a desired target distribution in mind, which I'll denote by rho bar. Rho bar will be a probability measure on RD. So in sampling, a fundamental question is how can we choose samples? So these are endpoints in d-dimensional Euclidean space, so that with high probability, they accurately represent this desired target distribution. And from the perspective of robot coverage algorithms, the question might be, how can we program our robots to move so that they distribute their locations, again, just in vectors in Euclidean space, according to this desired target distribution? The key difference between perhaps a sampling algorithm motivation and a robot coverage algorithm motivation is, from the robotics perspective, there would be a strong desire for a deterministic algorithm. And the reason why is, for a sampling algorithm, this sort of sampling process is typically, just done numerically. So, perhaps if it's something that just works with high probability, that's fine. You do a few runs and then you kind of pick the best result. But for a robot coverage algorithm, what you really want, you don't want to have to kind of drive the robots around multiple times in order to get them to the desired target distribution. There's some hope that you could get some convergence guarantees for a deterministic method so that it would perform well the first time. So that's the main distinction I'm making between these two problems. But in both cases, the fundamental goal is the same. We seek to approximate a fixed target distribution by an empirical measure. So here I have a Dirac mass at each of the locations, and then I'm weighting according to the number of either samples I've drawn or robots in my swarm. So in today's talk, I'm always going to be considering weighting these Dirac masses evenly, but everything I'll say works for, you can also allow them to have different weights, and that's fine. So it turns out that PDEs can inspire new ways to choose these locations or to construct this empirical measure, which guarantees that this holds. So first, I'm going to tell you about a classical PDE approach, which probably many of you know well. To talk about this classical approach, I'm going to put a stronger assumption on my desired target distribution rho bar. I'm going to assume that rho bar is log concave. What I mean by that is that rho bar is given by e to the negative v, where v is a convex function. So a classical example would just be a Gaussian, for example. Okay, so perhaps one of the best known PDE approaches in sampling is given by a Fokker-Planck equation. So that's the PDE I've written at the top here. It just describes the evolution of a density rho according to this. So when I write it in this way, it's divergence of rho, gradient log rho over rho bar. There's rho bar is my desired target distribution. It looks like a somewhat, potentially nonlinear equation. But it turns out that when you expand everything out, things get a lot simpler. And you can see that actually we just have a familiar diffusion term here, like in the heat equation. And then this is just a drift term. So we have a divergence of rho times the gradient of log rho bar, which we had up here. So when you write it this way, it's clear that it's actually just a linear equation. So we know a lot about solutions of this equation. For example, and furthermore, we know that solutions of this equation, because of this Wasserstein gradient flow structure that I'll describe in a second, they actually get close to your desired target distribution as quickly as possible in a certain sense, which is if you measure the distance or the difference more correctly between the solution of this equation at time t and your desired target distribution, if you measure the difference between these two things using the Kullback-Leibler divergence, which I wrote here, then what you can show is that the Kullback-Leibler divergence decays exponentially in time, where this parameter lambda is a non-negative number depending on the convexity of V. So if V is strongly convex, then lambda is strictly positive. So what this is saying is that solutions of this PDE converge to this desired target distribution really quickly. In fact, solutions of this PDE are somehow making the Kullback-Leibler divergence small as quickly as possible with respect to the Wasserstein structure, which I'll say more about in a moment. So because this is a nice linear equation with a familiar diffusion term, we can define a stochastic particle method. And using the stochastic particle method, we can show that the corresponding empirical measure converges to a solution of the PDE almost surely as n goes to infinity. Okay, so this is great. This is the classical approach to this type of problem, which is if we want to sample this desired target distribution rho bar, we know that solutions of this continuum equation are getting close to rho bar very quickly in this sense. And then if we do a stochastic particle method, we know we can approximate a solution of the continuum PDE by solutions of these stochastic ODEs. And so if you do this for sufficiently large n and for sufficiently long time, then you'll get what you want, which is approximation of this target distribution rho bar. Okay, so this is the classical approach. So today I'm going to be talking about a slightly different approach, which is instead of a diffusive PDE, I'm going to be talking about a PDE with degenerate diffusion. So at first glance, the PDE looks somewhat similar. So here it's again an evolution equation for rho, but instead of I basically just deleted the logarithm there. So, okay, again, when you delete the logarithm, you might think, oh, things get better. You know, that logarithm is probably causing lots of trouble. And perhaps it is in some ways, but a downside of deleting the logarithm there is that this is no longer a linear equation in rho. I'm not going to bother expanding this whole right-hand side because it gets a little messy, but I will expand it in a special case where your desired target distribution is just identically 1. In that case, if you expand the right-hand side, you get exactly this porous medium equation. So you can see this is Laplacian of rho squared. So this is no longer linear in rho. Interestingly, though, solutions of this degenerate diffusion equation still satisfy the same property as solutions of the original Fokker-Planck equation up here, which is that they still dissipate the Kullback-Leibler divergence exponentially quickly, where again, lambda depends on the desired target distribution. So a natural question might be that we know that the stochastic particle method is a really good choice for sampling and coverage algorithms based on its connection to this diffusive PDE. Could we come up with a particle method for simulating solutions of this PDE with degenerate diffusion? And would that also be useful? So the downside is that because this is no longer a linear equation, the principle up here of how you come up with this stochastic particle method completely breaks down. So the main goal of today's talk is going to be trying to see what we can salvage. Is there a way to define a particle method for this type of equation? what I'm going to tell you about is how you can use the fact that this comes from a Wasserstein gradient flow structure to not only define a particle method, but actually a deterministic particle method. So a bit different from what we had up here. So it's still a fair question. Why would you want to go all to this trouble to study this degenerate diffusive PDE when you already have this very nice familiar diffusive linear equation and a well-known particle method? So I'll try to give you 4 motivations that you might be interested in this second approach. The first is that this degenerate diffusive PDE has recently arisen in works in the sampling literature. First, because solutions of this equation have a connection to the dynamics of Stein variational gradient descent. A recent paper identified Stein variational gradient descent, showing that you can think of that as a sort of kernelized gradient flow, or as a kernelized version of this equation, where you sneak in a kernel right here, convolution kernel. Okay, so that's one perspective. Maybe perhaps by better understanding solutions of this equation and their corresponding particle methods, this can give us better insight into the properties of Stein variational gradient descent. A second reason that you might be interested in this equation is that just like the first equation up here, the Fokker-Planck equation, solutions of this equation are dissipating the Kullback-Leibler divergence as quickly as possible with respect to the Wasserstein structure in a way that I'll make precise in a few slides. It turns out that the second equation down here, solutions of this equation, are dissipating the chi-square divergence as quickly as possible with respect to the Wasserstein structure. So perhaps depending on what sampling model you have in mind, it might make more sense to be dissipating Kullback-Leibler or chi-square divergence. A second motivation for studying equations of this form comes from PDE. It turns out that this type of degenerate diffusion arises a lot in models of porous media or biological swarming. So perhaps being able to develop a particle method for simulating solutions will help in numerical methods for these types of PDEs. A third motivation comes from the robotic coverage. As I said, what I'm going to be talking about today is how we can simulate this with a deterministic particle method. So while a stochastic particle method might be fine in some contexts, in others, there's a large benefit of having something deterministic. And then finally, it turns out that the particle method I'm going to describe corresponds exactly to the mean field dynamics of training a neural network with a single hidden layer and radial basis function. Activation function. So perhaps by better understanding how this particle method converges to this degenerate diffusion equation, we can get more insight into the dynamics of training neural networks with a single hidden layer. Okay, so I've told you a little bit about my motivation. So now I'm going to tell you how we do it. How do we come up with this deterministic particle method? It's by using the fact that these equations have a Wasserstein gradient flow structure. So for the purposes of today's talk, I'm just going to stay at a pretty high level in terms of what is a Wasserstein gradient flow. I think many of you are very familiar with gradient flows in finite dimensional space. So, what is a gradient flow? It's just a curve that evolves in the direction of steepest descent of some energy, where the notion of steepest descent is induced by whatever metric you have in mind. So typically, you may have in mind like a Euclidean metric, or those of you in PDE or calculus of variations may also look at Hilbert space metrics like an L2 norm or H1 norm, H-1 norm. But in today's talk, I'm going to be interested in this Wasserstein metric. So here's a video that I think, due to Marc Pelletier, that I think illustrates a lot of the key properties of a gradient flow nicely. So first, of course, a gradient flow is an initial value problem. You have some initial condition, and then you want to look at the evolution in the direction of steepest descent of some energy. In this video, the energy is represented by this contour plot. But what I really like about this video is it helps you visualize the role of the metric, which in our case, we'll be thinking of as the Wasserstein metric. What the Wasserstein metric tells you is, on one hand, okay, you think gradient flow moving in the direction of steepest descent of the energy. So in other words, that just means it's sort of rolling down the level sets of the energy. But in fact, it's rolling down the level sets of the energy in a precise way. What it means to be a gradient descent is, in a sense, it's always rolling perpendicular to the level sets of the energy. And that's where the role of the underlying metric comes into play, is that it tells you what perpendicular means. Does it mean, for example, rolling that direction or rolling that direction? So what I like about this video is that it illustrates how you really need three things to precisely determine a gradient flow. You need the initial conditions, you need the energy, the ball is rolling down, and then you need the note, which geometry you're working with, which metric you're working with, that tells you how to roll down the energy. So it turns out that the two equations that I've already mentioned so far both have a Wasserstein gradient flow structure. So here's the first equation I wrote, the Fokker-Planck equation. This is a gradient flow of the Kullback-Leibler divergence. And so this is the sense in which solutions of this equation are exactly dissipating the Kullback-Leibler divergence as quickly as possible. They're the gradient flow of this energy with respect to the Wasserstein structure. Similarly, the second diffusion equation that I just mentioned, the degenerate diffusion equation, this is the gradient flow of the chi-square divergence. So solutions of this equation are dissipating the chi-square divergence as quickly as possible. Two other examples of gradient flows that will kind of turn out to be related in a moment. This is a really well-studied class of Wasserstein gradient flow because equations of this form arise a lot in, for example, swarming, mathematical biology. So here we have the evolution of a density according to, here we have an interaction term, then here we have a drift potential. And then we can see that arises from an energy given by a combination of an interaction energy and a potential energy. And then at the very bottom of the slide, here, all I write is the energy. I don't bother writing the dynamics because to me, the dynamics can get kind of long when you write it all out. But in a series of recent works, May Montanari-Nguyen, Roscoe van den Eyden, Shizan Bach, several recent works have recently identified the mean field training dynamics of a two-layer neural network as a gradient flow of this energy, exactly the loss. So here we have F naught, which is the function you're trying to approximate. We have nu, the data distribution, phi, the activation function, and then rho, this is what you're trying to train, the parameters you're trying to train. So, many choices of activation function arise in practice. For example, the ReLU activation function or a radial basis function activation function, as was kind of originally studied by May Montanari-Nguyen. So one thing I'd like to point out about this energy, that's maybe something kind of naive to point out, but it will be useful in what follows, is that you can write this energy here, which is in some sense like a new energy or an energy that's attracted a lot of attention over the past 2 years, in a way that's very similar to one of these familiar energies where there's been more substantial work done over the past 20 years. And that's just by, for example, expanding the square. So if I expand the square, I can rearrange the terms so that when I integrate out against nu, this just becomes a fixed function, k of xy. And then the cross term is here when I expand the square. And the cross term, again, I can integrate out against nu so that this becomes a fixed external potential, nu of x. And then the final term, I just pick up a constant. So the constant poses no difficulty when you're doing the gradient flow. Of course, when you take the gradient, the constant vanishes. This second term, because this is exactly a potential energy of the form up here, as has been well studied over the past 20 years, this also really produces no problems. So the difficulty is coming from this term. And the reason why is because in general, k depends on x and y separately. And that's very different from what we had up here. Here, an alternative way to write this energy would have been if I had written it as 1/2 double integral of k x minus y d rho x d rho y. And so the key thing here is that k only depends on the difference between x and y as opposed to x and y individually. However, in a special case for this choice of radial basis function, actually, indeed, it does just depend on the difference. So we can kind of rewrite this in a way that is very reminiscent of what we had up there. We can rewrite this first term as, if here's my radial basis function, the integral of psi convolved with rho squared d nu. Okay, so we'll keep this in mind because it turns out that this exact energy is going to appear again later on in the talk. Okay, so now I've told you a little bit about the Wasserstein gradient flow structure. So you know what a Wasserstein gradient flow is, and you know that these diffusion equations that we're interested in are Wasserstein gradient flows. But how does this help when it comes to particle methods? Where does the fact that these are Wasserstein gradient flows come into play? And so it comes into play for kind of two main reasons. First, it's that all Wasserstein gradient flows are solutions of a continuity equation. And second, it's that the Wasserstein gradient flow structure gives you good tools for proving Lipschitz estimates on your velocity field in that continuity equation. And that's exactly what you need for the continuity equation to be well posed and for you to approximate it with a particle method with a finite dimensional system of ODEs. Okay, so that's what I'm going to talk about now, is how this Wasserstein gradient flow structure helps you when it comes to these discretizations. Okay, so here are the three of the equations that I had on the previous slide that I was giving as examples of gradient flows. And the key thing to notice about each of these equations is that they're all of this form. They're all of the form time derivative of rho plus divergence of rho, plus divergence of rho times some velocity field, which in general can depend on rho. And in fact, you know, the velocity field is always given in this form according to the corresponding energy here. But the important thing to keep in mind is that they're all of this form. So I can define some velocity field so that every Wasserstein gradient flow is an example of a continuity equation. And continuity equations are really well behaved with respect to particle discretizations. And this is something that has a long history in PDE, stemming from, you know, kind of original work in fluids. So let me tell you about what I mean by a particle discretization and where the Wasserstein structure helps. Okay, so suppose that we have a continuity equation with a velocity, v of rho, and the key assumption I'm going to be making is that this velocity is uniformly Lipschitz continuous. And what I mean by uniformly Lipschitz continuous is I mean that that's uniform in the density rho. The same Lipschitz constant. So if you have an equation of that form, so here's the continuity equation, here's some initial data. It's at this point a classical approach to simulate solutions of this equation using a particle method, which is basically by a corresponding system of ODEs. So let me tell you what are the three steps to defining a particle method. So first step is that you approximate your initial data by a sum of Dirac masses by an empirical measure. The second step is that you evolve the locations in your Dirac masses according to the same velocity field. The key difference is that I'm now evaluating my velocity field at the empirical measure, which, you know, maybe sort of makes sense. Since up here I was evaluating my velocity field at rho, down here I'm evaluating it to evolve the particles at the empirical measure. So the really useful thing about particle methods is that it turns out that if the locations of your particles move according to this system of ODEs, that's equivalent to the empirical measure being a weak solution of this PDE. And so why is that useful? Because of this, we're able to put our particle method into the exact same mathematical framework as the actual solution that we want to approximate. And so because of that, we're able to use tools from the PDE level that are independent of our discretization, independent of the number of particles in our discretization to get convergence. So for example, in this case, when we're making assumption that V of rho is uniformly Lipschitz continuous, we're able to use kind of the standard stability estimates for solutions of this equation to conclude that the Wasserstein distance between this empirical measure and the solution of the continuity equation cannot expand faster then e to the Lipschitz constant times t times the Wasserstein distance between their initial data. Okay, so this is a useful estimate because now we know that as long as we improve this approximation of our initial data so that we choose rho n arbitrarily close to rho naught, we know that the solution of our particle method is going to converge to a solution of the original PDE. Okay, so so I've already mentioned that the particle method allows you to lift solutions of the ODEs into the PDE framework. This is very similar to how the Wasserstein distance itself lifts the distance on your underlying space to the space of probability measures. And I just to say one more time, where the gradient flow structure comes into play is that it gives you good tools for proving that V of rho is uniformly Lipschitz. In general, maybe it wouldn't be so clear how to do this, or this could be more challenging. But this is what the gradient flow perspective can help with. Okay, so how can am I done now? Can I use this idea of particle method to simulate solutions of this degenerate diffusion equation? So unfortunately, no. And the reason why is because these first two diffusion equations, the corresponding velocity field fails that assumption that I mentioned. It's not Lipschitz. But it turns out that this other type of PDE that has been well studied over the past 20 years, these velocity fields are going to be Lipschitz as long as, for example, the gradient of k or the gradient of v is bounded. And even weaker assumptions are possible if you maybe know more about your density rho. That this is as good as you can do if rho is just an arbitrary probability measure. Okay, so how can we somehow fix this? How can we fix the fact that this is not Lipschitz? How can we use the fact that we know how to do particle methods for this kind of equation to get a particle method for the degenerate diffusion equation that we have in mind? And so the solution I'm going to give today is to regularize. And so here's the idea. And in fact, this is literally the idea. This is how we did it piece by piece. Okay, so step number one is let's see if we can briefly forget about that rho bar. Let's assume that the rho bar is just identically equal to 1, so it's a uniform distribution. Then perhaps something you could do in order to make this energy look a little bit more like that energy is you could approximate one of those rho bars by a convolution with some sort of mollifier. So somehow, morally speaking, I'll put that in quotes because that has to be made precise. If you approximate rho by convolution with some, for example, a Gaussian mollifier epsilon, then as you remove that convolution, it should be converging to rho. And so, heuristically, this should be then converging to rho squared. So that's sort of good news because now this energy for epsilon positive is identical to this energy. And I said that the particle method worked down here as long as gradient of k was bounded. But okay, if phi is some Gaussian, well then sure, gradient of phi will be bounded, at least for finite epsilon. Okay, so that's the idea, is to somehow introduce an appropriate regularization so that we can discretize this equation by a particle method. Okay, so particle method plus regularization, and this is a regularized particle method, often known as a blob method, dating back to these classical vortex blob methods for the Euler and Navier-Stokes equations. So here is the original equation at the top that we wanted to simulate. And here is how we're going to modify it. So there was the original energy up here. And down here, what we're doing is we're sneaking in a convolution with a mollifier. So you can think of this as just sort of a modification of the energy. This is the, and then you look at the corresponding Wasserstein gradient flow coming from that. So what we're able to show is that indeed the velocity field here coming from the gradient flow of this energy is Lipschitz for all rho with bounded support. And the Lifshitz constant does deteriorate with epsilon. In general, this is as good as you can do if you don't know anything about your probability measure rho, except for that it has bounded support. That I'd say an interesting question would be if one could do better if you were somehow able to know more about rho, show that, get some a priori estimates on your solutions. But in general, this is as good as you can do, and this is fine for our purposes. So because we know that the velocity field is uniformly Lipschitz, we know that the corresponding particle method is well posed. So here I wrote the particle method at the bottom. For fixed epsilon greater than 0, as n goes to infinity, it converges to the gradient flow of this energy. Now an interesting connection is that it turns out that this energy I have here, this is exactly the same as the first term in that energy for the mean field training dynamics of a 2-layer neural network. This corresponds to exactly that in the case that the data distribution is given by 1 over rho bar. And so because of that, these dynamics that we're studying, these particle dynamics, correspond exactly to the dynamics of a 2-layer neural network in the mean field regime. Okay, so we know that everything is fine as long as epsilon is strictly positive, right? Because whenever epsilon is strictly positive, this is Lipschitz. So when n goes to infinity, this particle method will converge to a solution of this PDE. But the key question is, what happens when both n is going to infinity and epsilon is going to 0? That's really what we'd want in order to go from this approximate particle method to the original degenerate diffusion equation we had in mind. So there's been actually several previous works looking at this type of question. I think because I'm running towards the end of time, I will just touch on them briefly, and I'm happy to go back and discuss them further during the questions at the end. Maybe the most important thing is that all of the previous work has only considered the case of a uniform data distribution, rho bar identically equal to 1. So I'd say maybe the two key features of our work is that first, we allow for a non-uniform data distribution. And what we're able to show is that as long as you approximate the initial data of your degenerate diffusion equation really quickly. So this is I'm certainly non-optimal. We have to somehow be approximating this where the error between our particle approximation and the initial condition goes like little o of e to the -1 over epsilon to the d plus 2. Okay, so really fast. And as long as your initial data rho naught just has bounded entropy and compact support, then we know that we're able to show that our particle method converges to a solution of the degenerate diffusion equation. So like I mentioned, one key novelty is that we allow for non-uniform data distributions. And the second key novelty is that we allow for initial data with lower regularity. A lot of the existing results have required, for example, smooth and strictly positive initial data. The implications of this result in the 4 applications that I mentioned at the beginning. First, this gives a spatially discrete deterministic particle method for sampling according to the chi-square divergence. There's been some recent interest in that sort of thing. Perhaps this can contribute to that line of inquiry. A second is this gives a provably convergent numerical method for diffusive gradient flows with low regularity. We don't need the limiting solutions to be smooth and strictly positive to get convergence. It's a deterministic particle method, well suited to robotics. And then lastly, as I've said, it turns out that this particle method is equivalent to the training dynamics for neural networks with a single hidden layer, in this case of the RBF activation. because we are able to study this limit as n goes to infinity, which is the over-parameterized regime, and as the variance of your radial basis function decreases to 0, in the case of a general data distribution, perhaps this result can help shed some insight into the long time behavior, even for finite n and epsilon. So the limiting dynamics are the gradient flow of this energy. And this can be seen as convex in the Vasosine sense, as long as your data distribution is log convex and then the product of these two functions is concave. So it would be interesting to further study to what extent our result, which proves convergence as n goes to infinity and epsilon to 0 on bounded time intervals, gives any insight into the long time behavior of those particle methods, and to what extent they inherit the convexity of the limiting system. So I'll close by just flashing a few numerical results, and then we'll go into more detail and discussion. So, okay, so this is just for fun. You see the robots. I don't know if you actually can see them, but the little orange dots at the bottom, and then this is a kernel density estimate. The green is the desired target distribution. So, okay, you see convergence to the desired target distribution. Here we have only 20 robots, and over here, here we have 50 robots, and here we have 200, and same 50 and 200. So sure enough, more robots leads to a more accurate approximation. Okay, I'm saying robots, particles, whatever you prefer. In practice, we do really observe this exponential decrease of the KL divergence, even when the desired target distribution is not log concave. Also in practice, we don't need n, the number of particles, to scale according to epsilon in that insane way, like I said in our theorem. In fact, sort of more natural scalings make sense, and we can numerically look at the rate of convergence of our method, even though our theoretical result does not offer any rate. There's several directions for future work. One is to try to prove a theoretical result, quantifying the rate of convergence, seeing if we can recover what we've observed numerically. Second, can a better choice of radial basis function lead to faster rates of convergence? So, for now, we're just thinking of kind of simple radial basis functions like a Gaussian, but could a more intricate choice of that help improve the order of accuracy of our method, or the rate of convergence? And then lastly, our method is truly an interacting particle system. So a big downside of that is that the movement of each particle depends on all of the other particles. So if there's n particles in total, that leads to an order n squared computational complexity. But there's been some very interesting work lately done on the things like the random batch method, which are, in some ways maybe similar to stochastic gradient descent, and could some of these kind of incorporating some sort of stochasticity into our method allow us to lower the computational cost while still preserving this long time behavior. Thank you very much.
Right. Thank you, Katie, for this really beautiful talk. Questions? You can just speak up, right, if you have a question.
Hi, Kathy. Thank you very much for the wonderful talk. It's very interesting work. Hi. I have a question. I actually have two questions. It's kind of related. So for the theorem, so this convergence theorem, right? So I think on page 15 or something. Oh yeah, exactly. This page. Yeah, so I noticed in the bottom you have conclusion rho n, that when epsilon goes to 0, it converts to rho t. Does that depend on n or not? Is this true for all n, or?
So indeed, n and epsilon are coupled. And as epsilon is going to 0, n has to be going to infinity. And the way in which it's going to infinity is that it has to be approximating the initial data in terms of an empirical measure really quickly. So so this assumption here prescribes a rate at which n must be going to infinity as epsilon goes to 0.
I see.
Does that answer? So, and I don't claim that this is optimal, but I observe that slower choices of n going to infinity with respect to epsilon gives you perfectly good convergence results in practice. But yeah, I mean, this is, you know, this is what we could do now. So, but I think it would be, yeah, I think it would maybe be a different perspective on the problem. But yeah, still.
I see.
Probably
I
worth
see.
it to do.
Thanks. Thanks. The other question is on page 10, I think. Yeah, exactly. So I noticed that the inequality in the last line. So when t goes to infinity, the middle term will explode.
Absolutely.
Right. So
this is exactly why our convergence result only holds on bounded time intervals.
I see.
Now there's still, because I've mentioned that there are some cases in which the limiting dynamics are the gradient flow of a convex energy. I do believe that in some special cases you could get long time convergence, like convergence for all time and n, by leveraging this. But sort of in general, I don't think something like that is, yeah, in general, I think bounded time intervals.
I see. Thanks a lot.
Can I ask a question?
Go ahead.
Hi, Katie. Nice talk.
Hi.
So it mentioned some connection with the results on the training of two-layer neural networks, right? So I was wondering, it only applies for radial basis function. So
yes.
Can you say something about ReLU type of things?
I wish. Yeah, I mean, I think that's a really interesting question. Yeah, I think very interesting question. Yeah. So so now it's a bit different because, so, you know, radial basis function, we're looking as the variance goes to 0. So, okay, so what would be sort of the appropriate limiting process to be looking at for ReLU? But yeah, no, I think, yeah, no, there's, I think something that yeah, it is interesting question is how these sorts of ideas, maybe, you know, going from discrete to continuum for ReLU is maybe not as easy. So yeah, how could that be done? How could some more, yeah, is it a similar problem to this? Is it a similar problem how we couldn't discretize this right away, but we could with that? Or is it a different problem? But yeah, it seems like a really interesting question.
Yeah, I have one more question regarding what Kelvin asked about, which is the convergence result. So can you say maybe a little bit about the technique of the proof and maybe why do you need this exponential approximation for the initial conditions?
Yeah, this is kind of, also I'll tell you. So the technique of the proof is is this kind of gamma convergence of gradient flows. So the key difficulty in doing so, we prove it in 2 steps. And this will maybe clarify why we have that assumption on the initial data. Okay, so step number 1 is we use gamma convergence of the gradient flows to prove that solutions of this PDE converge to solutions of the top PDE, with an additional assumption that the initial data of all of these has to have bounded entropy. So that explicitly excludes taking particle initial data in this case.
Right.
So that's why you have to do the second step, is that you're approximating, then you have to use this Lipschitz estimate and use a stability estimate for fixed epsilon to say that, okay, if n is big enough, then a particle solution of this equation is close to the solution with the bounded entropy initial data, and then the gamma convergence case.
Right. Yeah, thanks. That really clarifies it for me, right? So if there are no further questions, I will invite everyone to the Gather Town. So as we have done before, right? So I just sent the link to the chat, right? And